Good afternoon, everybody. It's my great pleasure today to introduce Thore Graepel. Thore comes to us today from DeepMind, where he's been since 2015, and there he leads the multi-agent research team. Thore also holds a part-time position as chair of machine learning at the University College London since 2013, and he is also serving as a member of the board of directors at the Partnership on AI. Thore did his PhD at TU Berlin, and after that, he was a postdoctoral fellow at ETH Zurich, and that's actually where I met him 20 years ago. And I can attest that the place was all fun and games, because actually that's for the first time that I saw people trying to decipher the game of Go. Thore was one of the people there working on a 9x9 board and doing some great stuff. After that, he went in the Royal Holloway College in the University of London, and then Thore joined Microsoft Research in Cambridge in 2003, and there he co-founded the online services and advertising group. So major application of Thore's work include the Xbox Live's True Skill system for ranking and matchmaking, and the ad predictor framework for click-through rate prediction in Bing. And furthermore, Thore's work on the predictability of private attributes from digital records of human behavior has been the subject of several intense discussions among privacy experts and the general public. So when he returned back to, when he went to DeepMind, he returned to his original passion of understanding and creating intelligent systems. And he went well beyond the 9x9 board he was doing as a postdoc, and he contributed to creating the Alphago, which is the first program to defeat a human professional player in the full-size game of Go. I should mention also that Thore has picked up also acting. He participates in a film that I think he's going to talk about. But I have to say that I saw this film to my kids, and I finally got some credit because I pointed at Thore and I said, "Hey, I know the guy in the film." So I think their opinion about me got raised a little bit. So Thore, we're looking forward to your talk. And before you start, one last comment. I would like to ask the audience that if you have a question during the talk, please put it in the chat and I'll try to moderate these questions. Otherwise, please keep it for after the talk, when please raise your hand and we can go and ask Thore all the questions that we have. Thore, the floor is yours.
Great. Thank you so much for the kind introduction, Petros. Yeah, 20 years ago in Switzerland, glorious times back then. It's a great pleasure to be here. And I get to talk about one of my favorite topics, which is deep multi-agent reinforcement learning, how we can use it to build more intelligent systems. And in this particular talk, I want to focus on the topic of automatic curricula, which are an important lens through which we can view learning, because even machines need to get the right experience to learn from and need to get it in the right order, hence the name of that. I'd like to emphasize that this is joint work with some fantastic people at DeepMind that I'll point out at the appropriate times. To get started, of course, I'm sorry that for this very obvious reason, I'm not there in person and we can't all get together to meet in person. I hope that might happen some other time. But I'm also glad that as a community, we found these great ways of interacting together using technology. And so I will try to make the best possible use of that. So here's the plan for the lecture. I'll talk a little bit about my view of how to build intelligent systems, and then dive into the problems of one thing we call the problem, and the other thing, the autocurricula. And after that more general introduction, I'll go into 3 case studies. The first one about Alphago and later the application to chess in AlphaZero. as an example of such an automatic curriculum. Then I'll talk about learning in a video game in Capture the Flag, where we apply the ideas of automatic curricula as well. And finally, I turn to maybe the most difficult class of games, namely social dilemmas with self-interested agents, and see how these techniques stack up there and can help us study those types of systems. Good. So let's talk about intelligent systems. And the first question one might ask is, what is intelligence? And my colleagues, Legg and Hutter in 2007, came up with a definition of universal intelligence, the core of which you can see here in this equation. And it's basically quantifying the idea that intelligence measures an agent's ability to achieve goals in a wide range of environments. Let's look at this equation a little bit. The quantity on the left is a function of pi, and pi is a policy. A policy maps states or sequences of observations to actions, and is hence represents the agent that acts in a given environment. We see here that the intelligence of the agents is quantified as its performance over a range of environments. You see here the sum over all environments. Technically, this is the sum over all computable environments. And the V, mu pi, represents the value that policy pi can produce in the environment mu, which are the things that we're summing over. And then you see this weighting factor, 2 to the minus k of mu, and that represents, k is the Kolmogorov complexity of the environment mu. And you see here that effectively this measure weighs simple environments much higher than more complex environments. And of course, on the technical side, this weighting is also necessary so that the sum can converge here. So I don't want to go into the technical details of this definition too much, but rather take it as an inspiration for how we think about intelligence, namely in the sense of what I said earlier, that intelligence is this ability to achieve goals in a wide range of environments. So in order to understand this a little better, we consider the framework of reinforcement learning, which is basically a general purpose framework for AI. And it's based on the idea that we have an agent depicted here on the left that interacts with an environment depicted here on the right. It interacts by issuing actions to that environment, which then advances to a next state, which can be observed by the agent. And there's also a reward signal represented here by the star that tells the agent how well it is doing. The idea is that the agent is designed to maximize the expected long-term reward over its interactions with that environment. And among the people who work in machine learning, building these systems, the reinforcement learning framework, of course, is recognized as a very powerful universal framework for intelligence research. My colleague, David Silver, who was also the lead on the Alphago project, says reinforcement learning is enough as a formulation for the AI problem. And I think that's very interesting. It encompasses other forms of learning, for example, supervised and unsupervised learning as special cases. So that's the general framework that we'll be using. So why then are we thinking about multi-agent AI? What does that bring to the table? And I'd like to present 3 arguments why, if we think about intelligent systems, we want to talk about multi-agent systems. The first one is that we live in a multi-agent world. Artificial agents need to take into account the agency of other agents to succeed and to ultimately benefit us as human agents. The second argument is that artificial agents can be designed as multi-agent systems. If you think about an organization like Harvard or DeepMind, you can view it as an agent, as an intelligent agent, but it is composed of sub-agents. And that compositionality is something we can tap into when we think about how to design intelligent agents. And finally, the idea of automatic curricula. Human intelligence, even animal intelligence, did not evolve in isolation. And similarly, artificial agents can benefit from interactions with other agents and co-evolving with other agents. And I hope to show you in this talk how that works in practice and how we can make use of that. Let's dive a little more into these three areas. So multi-agent applications, this idea that the world is a multi-agent place. And we need to take that into account. Just think about traffic, the economy, how markets function, the workplace, sports, family. All of these real-world environments are multi-agent environments, and they require us to exercise skills like competition, cooperating with others, coordinating with others, communicating, predicting other agents' actions, or negotiating with them. And just as an example of how wired we are to thinking in terms of agency, consider the video on the right, which depicts an experimental study from 1944 by Hyder and Simmel, where they showed this video to demonstrate how quickly our brain picks up agency. Sorry, that one. Yeah, let me play that for you. So if you see this video, you basically just see a number of geometric shapes, very simple geometric shapes, circle, triangle, moving about in the environment. But we can't help but impose an interpretation on this where these elements seem to have agency. We almost seem to feel an urge to understand what's happening as a story. And so I just take this as a piece of evidence how ingrained the idea is that we think of our environment in terms of agents. And this is actually quite a cute story, so if you want to watch the rest of us, you can find it on YouTube. So the second aspect was this idea of multi-agent architectures. And in order to drive that point home, I would like to ask you, what do you think is the most intelligent entity in the world? And in the sense of the discussion, of the definition that I presented earlier. And to make that a little more concrete, we can ask, what if you picked any set of goals, you know, and think of these maybe as some of the goals that the sum is over in Shane's definition of intelligence. Build a bridge, cure a disease, make a movie, cook a meal, find a particular person. Who would you turn to if you wanted these problems solved for you? And I would argue you want to turn to the global market economy. That is the entity that will solve these problems for you if you can provide the appropriate incentives to it, basically money. And it is, of course, a highly complex multi-agent system, but it's not a single entity per se. And that's what I'm getting at here. It's composed of many intelligent sub-agents. To speak to the third point, multi-agent autocurricula and the co-evolution that comes with this. Really, our intelligence and animal intelligence evolved because there was competition with other species, with other tribes, with other individuals. But there was also the opportunity for cooperation, for hunting, gathering, sharing, learning from others, and ultimately the evolution of our culture, culminating in the evolution of mathematics, some would argue. And just to take a look here on the right, you see a plot from Robert Vogel where you see the time in years before now plotted on the x-axis and the human population on the y-axis. And of course, you see this exponential growth, in particular, taking off with the Industrial Revolution. And you see some of the highlights of innovations that have taken place. And you can see that, of course, human civilization, when suddenly there were so many humans, really took off. And there was this interactive process of more innovation, allowing more humans to be alive at the same time. And then those more humans driving more innovation. And some people would argue that it is really that we want to replicate when we create intelligent agents, almost like an intelligent civilization of agents. So what I'm taking from this is that it may very well be possible that artificial agents require company to become intelligent, that we need to let them interact with each other in order to create intelligent agents. So let me talk a little bit more about the problems that we need to solve in order to get there. And that is the problem and autocurricula. So our starting point is really an AI by learning paradigm. And what we mean by that is that we have a premise that we can achieve something like human level AI or high level AI through learning from experience. And that experience is basically data that we already have or data that we produce through simulation or real world interaction. And that we can have RL agents in this world, reinforcement learning agents, as depicted on the right, that can make use of that. But it requires us to solve three problems. The first one is the algorithm problem. We need to design powerful learning algorithms that turn experience into policies. Policies in the sense of the policies I talked about in the definition of intelligence. Those functions that map actions or sequences of observations, states or sequences of observations to actions in order to act in an environment. The second thing is we need to solve the problem because we need to design rich learning environments that provide necessary experience. Imagine you had a super powerful learning algorithm, but it lived in a very impoverished environment. Surely it wouldn't be able to develop more intelligent behaviors in that impoverished environment. Finally, the curriculum problem. To design efficient learning curricula in which the experience is delivered in the correct order to the learner, ideally with simple tasks coming before more complex tasks. And of course, this is very similar for humans as well, and in fact, inspired by that. So where could these rich world, this data come from that the agents would learn from? And there are essentially three possible solutions. We can learn from large amounts of real world data that we already have. YouTube, Facebook, Instagram, TikTok, Twitter, Wikipedia, Reddit. All of these data sources could provide the experience that these agents need. And in fact, that is an approach that many people take. For example, the language model GPT-3, which was so successful, of course, is trained on a large amount of text data. But here the question is, does that really work, or does acquiring intelligence not require interaction with an environment, experimenting with it? And in fact, I think that is probably true. And of course, the framework in which we work, reinforcement learning, is the one that supports this kind of interaction. The second possibility, of course, is to learn from interacting with the real world. Think about robots, chatbots, industrial control, where a system tries to, say, control a factory, and self-driving cars, of course. So that seems promising because the systems would immediately interact with the real world. But here the question is, can AI systems acquire enough experience in a safe and data efficient and cost-effective way? Because these learning algorithms at this time require a lot of data, and real-world interactions can be unsafe, they can be expensive, and they're often out of our control. We wouldn't want to just have put naive self-driving cars on the roads and just let them learn. They would just be, it would be too dangerous. So that means we turn to learning from interacting with simulations. And that's, in fact, the path that we've taken. And these can be video games or simulations of ecosystems, traffic systems, or dedicated AI training environments. And then the question for us is, can we design simulations that provide sufficiently rich and complex experience so that the systems that interact with them can acquire intelligence? So, and the remainder of the talk will in fact be about this particular paradigm here on the right. So what makes for a rich learning environment then? I'd like to propose a little thought experiment here in order to understand this better and to drive the idea that it is in fact multi-agent systems that could be useful here. And so the idea is that we design a simple game here. It's played on the board on the right, and one player places stones on the board, and the reward is the number of empty vertices that they would have surrounded. You know, let's think about a solution to this problem. Bang, there you have it. The maximum number of empty vertices have been surrounded. It's a boring solution. There's nothing rich or stimulating in it. Now consider the multi-agent or two-player version of this game. Two players take turns placing stones on the board and can capture stones. The reward is given to the player with more empty vertices surrounded at the end. And when you do that, you get the game of Go, and you get these highly complex strategies, open-ended, and a system in which expertise is almost unbounded and difficult to achieve. And what you see here, of course, is the famous move 37 from the second game of Lee Sedol against Alphago from 2016, which was the move that surprised many experts and was hailed as an innovation that the system Alphago had come up with. So we view the learning environment as a sum of two things: the substrate, think of the board, and the agents, the other agents. In normal reinforcement learning, it's just the agent with the substrate environment. But in multi-agent reinforcement learning, there are multiple agents interacting with the substrate environments. And that has the effect that one agent experiences other agents' policies as part of the environment dynamics. That dynamics then changes when other agents are also learning. So one agent's learning poses new training tasks for the other agents. And that's where the complexity comes from, the complexity that we want to harvest. And of course, you see here, this is of course symmetric. This is true for all the agents interacting with this environment. And I was just taking the one agent's perspective to make clear what that looks like. So there's, to support this view further, there's the social intelligence hypothesis. Social complexity is cognitively demanding and is thus the key selective pressure affecting brain size and by extension intelligence. And here's a plot by Dunbar where on the x-axis we have the neocortex ratio, effectively the relative size of the neocortex. And on the y-axis we have the mean group size of where these species of monkeys and apes live, and each dot represents a species. And you can see here the correlation between the size of the cortex and the group size in which they live. And so that might be taken as evidence that it is in fact the group size that can drive the complexity of an environment in a multi-agent system. And we want to make use of that for our AI systems. So what's the curriculum problem then? We want to design efficient learning curricula to deliver experiences to the learner in the right order. And there are two reasons for that. Many skills are easier to learn when other skills have already been acquired and which we call progressive learning, but also for exploration. Many situations or states are never reached unless certain skills are already present. And so you need certain basic skills in order to even encounter situations that you then master. Imagine you lose a game of chess already in the opening, then you'll never learn about the end game. That's the basic idea here. And to have an example here of a curriculum that might be close to home for you as mathematicians, here you see a plot over time, again, in years, of the different milestones of mathematical developments, how mathematical concepts have been developed. And on the x-axis, you see when they were originally discovered. And on the y-axis, you see when they are typically taught in a school curriculum. And you see that the order is roughly the same. And so it's that kind of natural curriculum. This is the order in which things have been discovered, but it's also the natural order in which to teach them, or at least one natural order to do that. So that's what we mean by curriculum and how these things follow one another. So basically the recipe that I'm going to talk about is that we want to create automatic curricula through multi-agent learning. We let multiple independent reinforcement learning agents interact in a common environment. And for any given one of these agents, the other agents provide the automatic curriculum through their own learning. And that allows us to explore different situations just by the agents doing best against that evolving environment. And it turns out that we need to create a diverse agent populations to populate the strategy space, if you like. And also these agents had better be aligned in their skills to avoid any imbalances. So these are some of the tricks that we'll be using. If you're interested in this more abstract view of things, I would recommend this paper that we wrote about autocurricula with Joe Lebo and others, which sketches out this conceptual approach further. Of course, we're standing on the shoulders of giants. I'm not going to go into the details here, but the idea of training systems in self-play has been around for a long time, since Samuel's famous checkers program. Here are some references of exciting work where this has been successful. So going forward now, I will present three little case studies about how we have applied these ideas. Learning chess with AlphaZero, which is a simple two-player, or simple, I shouldn't say that maybe, but which is a two-player game, zero-sum and perfect information. Then moving on to learning capture the flag, which is two teams playing against each other, two teams of learning agents. Again, zero-sum between the teams, but only partially observable environment. And finally, learning in social dilemmas. So let's start with the first one. Many of you have probably heard of this, the Alphago work. Here are my colleagues that were instrumental in making this work: David Silva, Thomas Hubert, Julian Schrittwieser, and Yannis Antonoglu, and others. And that's also the documentary that Petros was talking about and was published in Science in 2018. So what's the problem? In the game of Go, there's this gigantic game tree that we need to solve, because at any given position, the board is large and offers many possible moves, and also the game is reasonably deep. There are 200 to 300 moves to be played. And that was the problem that we were facing. And in the original Alphago, we had a data set of human expert positions, and then trained through supervised learning, what we call a policy network, that can that is a mapping from game states to a probability distribution over legal moves, and can allow us to sample plausible play inspired by experts. And then that allowed us to create a lot of games by self-play, just by letting the policy network play against itself. And from that, we were able to train the value network, which maps the board situation to the final outcome, or a probability of the final outcome, if black would win or if white would win. And so once we have these self-play games, both the policy network and the value network are simple supervised learning problems that we could make use of. And then how do we use them? This is a little cartoon of the game tree in the game of Go. And the policy network allows us to make that game tree more narrower, because we only need to consider the plausible moves in order to search it. And that's clearly helpful for reducing the search complexity. And then the value network allows us to stop the search at some point and evaluate the position rather than playing all the way to the end, as in Monte Carlo approaches, to sample the outcome. And again, that reduces the game tree complexity and allows us to search this tree more effectively. And of course, you guessed it, or you read it in the paper, this AlphaGo system indeed won 4-1 against this absolute Go champion, Lee Sedol, who's a 9-dan professional and who's by many considered to be the Roger Federer of the game of Go. And it was, of course, remarkable also that he won one of the games. He's a great champion, and he found a remarkable move to really confuse our system at the time. And we have the highest respect for him as a player. But of course, we wanted to generalize this idea. So the older system still relied on human data, on human game features, and also was only applicable to a single game. And we were wondering, can we apply this approach also to other games? And here we used the games of chess, shogi, and Go to test out that idea. And you see some of my co-authors here listed for this paper. And so here the idea is to really only use self-play and start from zero knowledge, hence the name AlphaZero. So we again have a policy and a value network indicated here by P and V, but we randomly initialize them. So initially the system has no idea how to play this game. And now we do self-play and we produce a data set of games by combining the policy and value network with a game tree search, as indicated here, to produce the moves, to produce many, many games. And those games were bad Go games. I mean, this system had no idea of how to play, right? But they give us a start for our bootstrapping process. Because now that we have these games, even though they are very weak Go games, we can train a new policy network, P prime, on these games. And the idea is just to take the games that we've now generated, and they give us pairs of state and the action taken, and we can train a classifier or the policy network from that data, which might now be making slightly better predictions than the first one. Similarly, we can train a value network V prime on this data because we can sample a position from it, and we can look at the outcome of that game. And that pair can now be used to train the value network, again, using the equivalent of supervised learning. And then, of course, the iterative power of this method is to reinsert P prime and V prime, the newly trained networks, into the tree search and keep going and generate new games, now at a slightly higher levels, because both the policy network and the value network are now better than they were before. And you can think of the tree search as always acting as a policy improvement operator that we're leveraging here.
Thore, there is a quick question by Mustaba Alam. I'm not sure if Mustaba could unmute and give the question.
Oh, yeah, I can unmute myself. Would you like me to ask it?
Please.
Okay, yeah, you said the policy network in the non-zero case tends to search through plausible moves. Is this based only on human expert moves, or do you initialize it with human expert moves and then going forward include moves of other agents?
Yeah, in that first version, in the AlphaGo version, it was really that we had a few 100,000 game records of human expert players, and it was basically trained by imitation learning as a multi-class classifier on the move positions given the game position. That's all it was at the beginning, and that was actually already a pretty strong. That neural network alone was already strong enough to beat me, and I'm a 1-dan player at the game of Go. So that pure imitation learning already yielded a strong player, but of course it's boosted in many ways by the tree search and the value network.
Okay, so moving on to the more recent zero case,
Maybe we can keep it for later, Mustafa.
Sure. Sorry about that.
Okay? Yeah. All right. Yeah.
Yeah. Let's move on.
Yeah.
Right. Thank you very much.
Thank you.
So here we see how this system fared as a function of the number of steps it took in training. And for example, top left, you see in chess, the system took only 4 hours to achieve this playing strength of Stockfish, which is a very strong, maybe the strongest at the time chess engine that works according to traditional principles. And so the system worked very well for these traditional board games, including chess, shogi, and the game of Go. Here's my favorite position. I assume there are some chess players among you here, which people on YouTube termed the immortal Zugzwang game, where AlphaZero with white played against Stockfish with black. And you can see here that white has achieved a superior position. Black is all walled in. There's a very strong attack by 3 pieces of white that have converged on the pawn on f7. Also, black's queen is in that corner and cannot get out. And this is a position where any move that black makes actually leads to a disadvantage. And so if you go through the pieces that that black could possibly play here, you know, they either cannot move, or if they do move, the consequence is that black loses a crucial piece and loses. So a typical Zugzwang position that AlphaZero was able to maneuver Stockfish into, where Stockfish is a way superhuman system based on traditional tree search. Cool. So you can see there is really this element of automatic curriculum that is crucial to the success of AlphaGo, AlphaZero, because it starts off very weakly and it always plays against itself, which means it always plays at a balanced level in terms of skill, and then progresses step by step by bootstrapping itself out of random play to beginner's play to absolute expert play. Through this, and in the process, it discovers new knowledge about the domain that it's operating in. Of course, there are many open questions about other game types, more than 2 players, imperfect information games, games with larger action spaces, and so on. So lots of work to do there. The second case study I'd like to talk about is learning to play Capture the Flag, which is a video game. And as such, of course, in many ways more complex. And this is joint work with Max Jaderberg, Wojtek Czarnecki, and Ian Dunning, and others, and appeared in Science 2018. And so just to understand what this game is about, let me play you a quick video and explain what this works, how this works. So this is the perspective of the agents. It's a first-person perspective, but we show you here the top level so that you can see what's going on. So the goal of the game is for the agents to pick up the opponent flag and carry it back to their own base. And then they score if their own flag is still there and they can score. But an extra complication is that their flag might not be there. But so what they need to do is they need to capture the opponent flag and then make sure that their own flag is at home, and only then can they score. And that makes it a game in which team play is very important. So the overall procedure here is that we train a population of agents. And we do that in a variety of arenas. You can see on the right here that we procedurally generate a very rich set of different environments in which this game takes place. And then we have a population of agents, and we pair them against each other in these arenas in different combinations. And so through that, each agent grows up, if you like, and learns from a wide variety of different strategies in a wide variety of different environments. And it is this process that allows them to become better and better at this game. You can see here on the right how these agents become better and better. The agent's ELO number, that represents their skill from a pairwise estimation procedure, goes up as they have more and more training. And the agent that we've built here through the system I just briefly described in fact turns out to be superhuman, not necessarily super pro-human, but with the collection of people we had for testing. And we were particularly happy to find that humans rated our top agent to be a better collaborator if they played with it, when they played with it in a team, than some of the human teammates. And so it seems that the system was really sufficiently adaptive and strong at the game that humans like to actually play with that system as a partner. So there's a whole other dimension to that project, and I'll just give you a glimpse of it. But we can now look into the agent's neural network and look at its latent representation of the state that it is in. So imagine this agent perceives the world through the videos, first-person video that it sees, and it somehow needs to make sense of that world. And it represents the internal state by a high-dimensional vector, think about a 1,000-dimensional vector. And what you see here is a 2D projection of that vector, to down projection to 2 dimensions for interpretability using what we call a t-SNE embedding. And we've colored here different game states that make sense to humans when we interpret them, such as flag is at home, opponent is in base, and things like that, according to colors. And we see that the agent similarly has made sense of the game state in this way because it has these coherently colored areas in its state representation that it considers to be similar, and where it presumably draws similar policies or actions for these different situations. And the agents produced very interesting results. They defended their own home base. They did opponent base camping, so they waited in the opponent base for the flag to reappear there so that it could steal it. Or they worked, as you see on the right, as a team and stuck together so that they would be stronger together than if they were separate from one another. So again here, what's crucial is that we have this agent population. It's a multi-agent system. They're training against each other and adapting, and they're becoming better together. They're co-evolving in their skills, and that enables any one agent to become better because it's surrounded by other agents, either co-players in the team or opponents, and that raises the level of the overall population through the learning that's going on. So turning to the third.
Thore, there is one more question from Charles Fadel.
Oh yeah, go for it.
Charles?
I've typed it into the chat, so perhaps it's easier to be read.
So Charles' question, he says the results are amazing, but he has this question, is there something disappointing about the system's performance saturating, even if it is beyond human capabilities as it is?
Yeah, so yeah, that's a very interesting question. And I mean, this is such a short segment that I wasn't able to put forward the necessary critiques of the system. But so that could be a function of 2 different things. It could be that the game just isn't deeper than that. So that, you know, at some point, the complexity of the environment is just saturated, and there are no cleverer ways of playing it, if you like. That's probably not the factor determining it here. I think it's genuinely that the network capacity of these agents is limited, and that they may not have discovered better strategies. So effectively, they might be in some kind of local strategy optimum here, from which they can't further advance. And we would like to throw more computation at it, but believe me, these systems already consume a lot of compute resources. But it is possible that if we threw more compute at it and also maybe increase the number of players, that there could be some further advances here. It's a great question. Yeah, we've seen it saturate every time in all of the games we've tried. So it's maybe not a completely open-ended environment in that sense. Cool. Thanks for that question. I'll move on to the third case study, which is about learning in social dilemmas. And this is joint work in particular with Julien Perola, Joel Lebo, and others at DeepMind. And social dilemmas are a super interesting situation for RL agents because there are situations where any individual may profit from selfishness unless too many individuals choose the selfish option, in which case the whole group loses. And there are many examples of that: the tragedy of the commons, public goods games, free rider situations, say in public transport, resource depletion. A lot of our civilizational problems are at heart social dilemmas. And the main question is really, how can cooperation emerge despite this adversarial game formulation where selfishness is actually the thing that collectively leads to doom? And the particular type of problem is that of common pool resources like fisheries or groundwater basins or irrigation systems, because they have two properties. You cannot quite exclude others from using a resource, and they are subtractable. The more users there are, the more of the resource will be consumed. And these two properties make managing such common pool resources particularly tricky. And Elinor Ostrom actually received a Nobel Prize in 2009 in economics for work in this, where she looked at how human communities can address this problem. So if you're interested in that type of work, I'll recommend that you look at her work. So here's just a little plot of how our game works that we've designed to study these problems. We call it the commons game. And agents move around in the little grid world. It's a 2D world. And there are apples growing there, and agents want to eat apples. But the apples have the properties that if all of the apples in a particular patch are harvested, no more apples regrow, whereas otherwise they do regrow. So there's a question of sustainability in these systems. The agents also have a timeout beam to exert some force on other agents as well. And the agent basically sees a local view of this environment, as you can see here on the right. And so we tried this. Imagine the game on the right. There are 12 players, and each agent individually wants to eat as many apples as possible. But due to this effect that apples don't regrow unless there are some apples left, we have a tragedy of the commons situation. And we plot different outcome metrics, not just the utilitarian efficiency of the system, but also equality, sustainability, and peacefulness for this system at work. And I'll show you some videos what that looks like. So if you consider the video on the left, early in training, harvesting is sustainable. These 12 agents just run around and eat green apples. The red ones are the agents. And the apples can regrow. Why is it still sustainable? Because the agents aren't actually that good at it yet. They're still learning to do it. If we now move to later in the training, as you can see in the middle here, these agents have become very good at harvesting apples. And now the apples are quickly gone. Entire patches are harvested. And the tragedy of the commons kicks in because these apples are not regrowing. And so this collective of agents is effectively destroying the basis of its own well-being. And then finally, later on in training, harvesting becomes more sustainable again. It's not for a great reason, unfortunately. The agents have discovered their zapping beam in order to take out other agents effectively. And that makes the overall process less efficient. So everything is more sustainable in a way, but at the same time, we've lost the nice property of having a peaceful collective. So this is just an example of how these things play out. And you can see here some plots of these 4 different quantities. And you see between 1,000 and 2,000 how the efficiency really drops because these agents become really good at harvesting, which means they're over-harvesting and sustainability is lost, whereas later in training, they regain some of that sustainability. But of course, in the bottom right, you see peacefulness, and that drops because they've discovered the zapping beam. Good. So these are some sketches of the types of outcomes that we see. There's also an interesting aspect that we studied, which was the idea of what would happen if we had one agent that has this zapping beam and others don't. And that agent can exclude other agents from their area. Would we then have more sustainability in that area? And it turns out that that's in fact the case. You see the trained agent here. One of these agents is able to zap other agents away, if you like. And that's that little flash you see. And that agent, in fact, is able to defend the lower left area as its territory in a way. And because it's its territory, it can just carefully harvest it and achieve some degree of sustainability in that area, whereas the other agents are not in great shape because they don't have their own area to defend. And you can see here in the plot at the bottom that where we plot the individual return of agents versus how widely they range over the area. And you can see here that the zappers have higher individual return because they can defend their area, but they're all also spatially more located because they stick around their area that they defend. Whereas the non-zappers, they have no fixed territory, they move around, but don't actually get great individual return from that. Okay, so we want to finish at 7:30, is that right, Petros?
About that time would be good, yeah. So we can have a few questions after that, yeah.
Let me just move to my conclusions then, so that we have some time for questions. So here we showed that in this most challenging set of multi-agent reinforcement learning settings, which are called social dilemmas, it's actually really tricky for the agents to find sustainable solutions. And it turns out that there are some indications in these results that there is the emergence of exclusion, of excluding other agents from a particular region of the map or a particular set of resources, some form of privatization, if you like, and that really gains an advantage, of course, for the agent that can exclude others, but also locally makes it possible to have a more sustainable harvesting policy, of course, at the cost of increasing inequality. But more broadly, we think of these social dilemmas as very rich social situations in which automatic curricula could emerge, because it is really these social types of tensions that presumably have led to a lot of the increase in human intelligence based on this social intelligence hypothesis that I had mentioned earlier. Good. So overall, stepping away now from the case studies, the way ahead is really that we're looking for further evidence that multi-agent learning is an important key to unlocking more generally intelligent systems. And part of the game is clearly that we want to create richer substrate environments and design the interactions between the agents to be ever richer, so that we can get more complex environmental interactions. And as a consequence, the agents, should their learning algorithms be strong enough, can pick up more and more intelligent behaviors. Also, we're interested in the collective level. So you can think of these agents that interact as forming some kind of artificial agent society. And it's fascinating to see what kind of collective behavior emerge. Can there be norms that emerge among these agents? Punishment, maybe, or other things that we know were the key ingredients in how human collectives operate. And so I think those are really exciting questions. And I'm looking forward to a future where we build these artificial societies with more and more agents, where they can stimulate each other and also collectively discover new patterns of behavior and presumably more intelligent patterns of behavior. Yeah, that's it from me. As I said, a lot of this work, of course, due to my fantastic collaborators at DeepMind and elsewhere. Here are some of their names for the different segments of the talk. But I'd be very happy to take questions now. Thanks.
Yeah, thank you very much, Thore. This was amazing. I'd like to share one of the comments that we had from Bonnie Ring here. It says, "Wow, that's fascinating," and indeed it was. There's a few questions that people could start raising their hands. I promised to Mujtaba that he posed one of the first questions, so I said he can ask this question at the end. So Mujtaba, please go ahead again.
Yeah. So mentioned how intelligent systems can really, near the beginning, you mentioned how intelligent systems are basically in the end meant to interact with humans. So going off of that, I noticed in the case of Go, both Yoshida Ishida and Lee Sedol both attributed a great improvement in their game to their time with Alphago. So is there any research in multi-agent systems whose goals aren't necessarily to maximize the performance of the whole system, but to maximize the skill of a specific agent by creating an optimal curriculum for that agent, the human?
Yeah, that's a great question. We were also extremely happy to hear the feedback from first Go players for AlphaGo and later also chess players, that they were actually able to learn something from the games that AlphaZero produced. And there was even a book that appeared, if you're a chess player, it's called Game Changer, in which two chess professionals analyze AlphaZero chess games and draw lessons from them and contrast it with the history of chess. And the reason, of course, that this is possible is that these are zero-sum games. And that means that there is some kind of, or maybe a second property of them is that there is some kind of transitive skill directions. So you can really do pairwise comparisons, and they form at least some kind of partial order of skill, where some policies are better than others. And that's universally true for humans playing and for agents playing. And so if agents in self-play make progress along this axis of getting better at the game, then that effectively means that for humans, that's the same axis of getting better, and they can immediately benefit from the innovations being made. And you're correctly pointing out that that might not always be the case. For example, already in games with more than 2 players, it's not so clear, because we then may not have a unique Nash equilibrium. There's an equilibrium selection problem there. And it could very well be that through self-play, these agents arrive at one equilibrium, and humans would really want to play in another equilibrium, and they would get no guidance whatsoever from what has been learned. And so that's a complex set of problems there. And one way out of this, of course, is to think about, can we design these agents to specifically be good at training humans and helping humans? And to some degree, that's being addressed by explainability research. So, for example, we can try to extract rules from play that has been developed by these agents. For example, we can do a game tree analysis and have humans learn from that. But there has also been work where agents try to explicitly benefit the human, in the sense that they try to figure out what the objective or reward function of the human is through a process we call inverse reinforcement learning, and then try to optimize for that. Regarding direct curriculum learning, I'm not so familiar with the literature, but I think there have been attempts at that. But the problem is it very heavily relies on interactions with humans. So probably platforms that teach, like maybe Coursera or something like that, or online platforms for pupils, would be in a great position to gather data and also experiment with different interventions of how to produce material or provide material to the pupils in different orders, and see which ones are the most effective ones for humans. I think this is a super interesting question and could be really valuable for online education, which is a big thing in particular this year.
Okay, we have the next question is from Charles.
Thank you, Petros and Thore. This is fascinating. And by the way, I am myself in education. We're developing, among other things, a course on game theory. So could not have been better timing. One of the problems you see, of course, is the more scarcity, the higher the price. And so it's only an incentive for a poacher to kill all the sturgeon or all the elephants or all the whatever. So what this made me realize is that what you're dealing with is an n-dimensional game of n curves. You know, you have all of these n curves, and they're all partially orthogonal to each other, and they have slightly variable shapes, and they may be randomly moving or wobbling a bit. And even a brilliant system cannot find a way to completely come up with a real good, stable solution. So what the brilliant system is actually doing on its own, seemingly, is to realize the only way I can deal with this is to simplify the problem in the first place. So I'm going to go and have my shooting agent simplify the problem, and then I can deal with it, which is what we do with poachers in reserves. But this is really profound because it goes to the understanding that any system can be complex, but not overly complex to be treatable. So you want to have, like Einstein said, something that's elegant, but not simplistic, which by itself is an N curve, by the way. It's like the wisdom N curve about making the system at right size. So you can deal with the parameters, but Pareto them and don't deal with an infinity of them, just the essential few that have the, let's say, the nodes of action in that a series of feedback loops. Am I correct?
Yeah, I think that that makes a lot of sense. I mean, you're quite right, picking up on the point that, you know, the system is wobbly in the sense that, you know, these things are shifting around, and there's now even a theory developing, you know, you probably know better than I do, but in game theory, we pay a lot of attention to the notion of equilibria. And partly because they're tractable and they're elegant, but there's also serious limitations there, because what happens if there are multiple equilibria, for example, and agents then don't know which one to enter. But there's this new set of results where people look at the dynamics of learning agents, and they basically think of the game together with a learning agent as producing a dynamics, and that's a trajectory through the policy space that continues to evolve. And so really, in that view, the game is not characterized by an equilibrium, but it's characterized by the dynamics of that system. And you can study things like limit cycles and periods and so on of that dynamical system now. And now you describe this game in those terms. And that might well be more realistic, because that's what you get when you have adaptive systems that interact with that game, rather than an abstract analysis that makes assumptions about rationality and, you know, mutual assumptions as made in game theory. So I think that could be a very rich view, and also a very rich set of mathematical problems that arise when you take this view that games really game plus learning algorithm defines dynamical system.
Thank you, Thore. The analogy that came to mind as you were describing the multiplicity of stable states is like so I'm an electrical engineer, so I think of, for example, a pendulum dancing around a bunch of magnets. There may be plenty of, like in feedback control systems, you have these nodes of equilibrium, these resonance nodes, but there may be plenty of them, and a tiny bit of instability in the system will bounce you from one to the other because you don't have enough of a potential well to stay in that potential well. So
Raphael, Charles, I'm sorry. There is one more question lined up, and I'd like to take this last question from Raphael, and I think we took a lot out of the time of Thore. Raphael, please.
Thank you, Petros. Yeah, I realize my question might be a bit tangential and a bit general. So, you know, if it's already over time, you feel free to skip it. But I wanted to ask a little bit about the cost of those computations, because when we see the training, it doesn't look like, you know, it looks like it's just a few iterations and it's not that costly. But on the other hand, I mean, I've heard that usually training those systems can be very costly computationally, and my question is very broad. It's like, do you have strategies to try to reduce this computing costs? You were mentioning during the talk that like some of the methods you have is to throw even more computation, but maybe do you also have some methods that like make it more computationally efficient?
Yeah, that is a great question. I'm very happy to answer it. In general, if we have a few more questions, I don't mind. I'm not constrained time-wise. But so these are very expensive methods. Why is that? Well, we have first of all, a single agent can already be relatively complex because there's a neural network with millions of parameters typically. That need to be tuned during training, and doing that, you know, we do that on graphic processing units, you know, GPUs, and we also have special hardware on which we do that, and so that is very expensive. Now, also the environments, you know, if you think of running a game like Capture the Flag, those need to be rendered, so there's an additional factor of cost there, and then finally, these agents also need to execute within those environments. And that's inference through the neural network, not training, but, you know, just using the given neural network with its weights. And there you have an additional cost of generating this huge amount of experience. And so computation is a huge concern. And we always try to do things as efficiently as possible. There's a trade-off between human time of development time and cost for computation, and that also needs to be weighed. So any investment in trying to make things more efficient also costs human time to do that. But it is making it more efficient is also part of the research, because we know that humans are so much better at learning from fewer examples. And so we know that these deep reinforcement learning algorithms take by orders of magnitude more examples to learn any given thing. And data efficient learning, therefore, is really also a core part of what we're trying to do in deep reinforcement learning. And the question is, how is it best achieved? And one thing is, can we equip the agents with better prior knowledge so that they need less experience to come up with a good policy? Other questions are about representations and abstractions. Can these agents develop? Can we put architectures together that are better at developing abstractions that are useful for learning? And there's also the notion of transfer learning, the idea that something learned in one environment should be reusable in another environment. For example, if these environments have key things in common, like the spatiotemporal structure or the action spaces or other things, or the types of objects in the environment. And then you would hope that something learned in one environment can be reapplied in the other one. Hence, training on the second environment should be much cheaper than the original training on the first environment. And are very active areas of research, but progress has not been great there. It's these are really very difficult questions, and the better we can answer them, the closer we'll come to truly intelligent systems. So it's firmly on the agenda, I would say.
When you say no big progress, you mean like nothing that has gained like an order of magnitude, or nothing that has gained like several order of magnitude in efficiency?
Yeah, it's almost worse than that. You know, for example, there's the problem of, we call this continual learning, when you first want to learn task 1 and then you want to learn task 2 based on task 1. And you'd hope that you can learn task 2 faster. But the truth is that these current neural networks often are still struggling with still retaining task 1 if they then train on task 2. You see, you first train on one task, and your hope is that it'll be easier to train on task 2, but then you train on task 2, but the system loses the ability to perform on task 1.
I see. Yeah.
And we call that catastrophic forgetting, and it's one of the big problems in continual learning, because the new aspects of the learning task tend to destroy the patterns in the weights of the neural network that have been learned for the purpose of mastering the first task. And so often these systems need to end up feeding a mixture of experience from both tasks, so that the new task can be learned, but the old task is not forgotten. And of course, that then is more training and requires more computation again. And so one big question is, how can we create systems that first overcome this problem of destructive interference of these learning processes, so that they don't suffer from catastrophic forgetting, but that also can benefit from what has previously been learned in order to learn the next tasks as humans can do.
I see. Thank you.
Gustavo?
Hi, yes, this actually builds on what you were saying about catastrophic forgetting. In Alpha 0, did all of the agents use only the most recent policy/value networks, or did some of them use older or modified ones to prevent backsliding or some sort of strategic brittleness? Sorry.
Yeah, that's a great question. So I actually showed a bit of a cartoon of the process. So what's actually happening is that this is a continuous process. So the two processes that I talked about was creating new experience by having the system play against itself, and then training the policy and value networks on this experience that has been created. But what in fact happens is that these two processes are running concurrently, and the self-play process, where the system plays against itself to produce data, feeds into what we call a replay buffer, a buffer of experience on which that other system, that learning system, then draws. And then now this allows us to reason about the question that you're asking, namely, what should be the window of freshness that we have on this pool? Because we can forget older experience, or we can retain it. And it is in fact the case that we want to retain some of the older experience, so that we don't just always have the latest system playing against each other and learning from that, but also learning from some of the older experience. And in fact, we had a situation, I think there's a pattern called a ladder in the game of Go. And that's a pattern that is never actually played out when both players master it, because it's disadvantageous for one of the players to be guaranteed. Either the ladder works or it doesn't. And if it works, the other guy doesn't play it. And if it doesn't work, the first guy doesn't try it. And so in the data, you never see the ladder. And so the system then forgets about how to handle it. And it can be a difficult concept to acquire for such a system. And then the trick is to play with that replay buffer and see how much of the old experience is best retained for retraining, so to make sure that the system doesn't forget about these things.
How much was necessary? Was it like the square root of total learn time, or some factor, or what? I'm not, like, was it, what kind of function did you, and what kind of function ended up being best in terms of the ratio of the buffer to the total time spent learning?
It's a good question, but I can't recall. I think we had some sampling scheme that made older experience less likely to be resampled than new experience. but I don't recall that. Can I refer you to the paper, please?
Yes. I'm sorry about that. Yeah, sure.
Take a look at.
Thank you very much.
Thanks.
I think, Thore, we can keep going with many questions. I have many myself, but I'll keep them for a private session maybe. It was fascinating. It was a very diverse and great audience. So thank you very much again for this fascinating talk, and we hope to see you again soon in person.
Great. Thank you very much for having me, and thanks for the questions as well.
Great. Thank you.